G'day all, I've got a question regarding method of joints that I'd like to share with you. Method of joints is just one of those things that it's a process, and if you overthink it can become complicated, but if you break it down into steps it's relatively simple and straightforward. And so I encourage you just to follow the steps that I do when I go about solving these truss problems. We're going to begin, very first thing that we do whenever we are solving these problems, we're going to draw a free body diagram. Prepared one here a little bit earlier, so I'll throw that up. And here's our free body diagram. So you can see that we've got the external forces of the truss, BY, AY and AX, and we also have the force from up above, that 3 kilonewton force that's coming down on the center point at the top of the apex of the truss there. But then we've sort of educated guessing, I suppose, what the internal forces of the truss might be doing. Now, if we just have a look at this 3 kilonewton force coming from the top section here, it's pretty easy to identify, well, there must be these other forces here that are pushing back up to counterbalance that, because remember, when we're talking statics, we're talking about equilibrium, nothing's moving, and so therefore if we don't have these counteracting forces, we're going to get movement, and we don't want movement in a static structure as such. So that's quite important. Coming back down, looking here, we've got our support reactions that come from these supports here. Those support reactions, obviously they're going to be pushing back up, because if we've got these forces here, or the force of the truss, that 3 kilonewton force and other forces pushing back down, then we're going to need to have these forces here pushing back up in order to maintain that static equilibrium. I can fairly well assume that we are going to have the forces here going in this direction, in the upward direction. Coming across here, looking at the AX, if we go back over to here, we see here that we're going to have this pinned joint here, or the pinned support reaction, if you like, this fixed reaction, support reaction. It's going to have that X and Y force locked. Okay, when you come over to this one here, we're going to see B reaction. It's a roller support, so therefore it's going to be allowed to move in this direction and back in that direction. But we are going to have that Y component, or that Y force, that's going to be pushing back up in order to keep it from falling over, if you like, or causing some type of catastrophe. So that's what we've got going on. And I would think, looking at this, if we have a triangle with forces pushing out here that we have, then you're going to need some sort of a tension force here to hold that bottom chord back in, to keep it from spreading apart. And so I've assumed that that's the direction. Now, if by chance that wasn't to be the direction, that's no big real deal, because the sense, or if you like, the negative, if we get a negative in the answer, then we know that we just simply need to switch the sense of that direction back around the other way. But I'm fairly confident, looking at this, that that's the way the forces will be acting in this here truss. Okay, so let's start. We'll go forward now as we're resolving what the support reactions are. That's a pretty straightforward process of doing that. And so what we're going to do, we can take moments about point A. So we're going to sum the moments. I'm going to call it in this positive direction of moments around point A, and we know that it's a static structure, so therefore it is going to be all equal to 0. Okay, so that's pretty easy, that little bit. Now it's doing our moment solutions. We see that we have this force. We can see we've got this 3 kilonewton force up the top here that is acting halfway. So we've got 3 meters across the bottom there, in that bottom chord section. We've got that 3 kilonewton force which is acting halfway along that, which is going to be naturally 1.5. So what I'm going to do here is go, okay, well, we've got the 3 kilonewtons multiplied by our 1.5 meters, and that is going to be causing a positive moment. Why is it causing a positive moment? Because this is pushing down past here and it's forcing it to go around that way, just like our direction of our symbol that we've put up there, the arrow symbol that we've put up there. So that's going to be positive. Next, I'm going to add in 1.5 the BY support, because that's going to be, we're not going to include A here, because on that one there we're taking it around that point. So if we're taking it around that point, we're not taking through the point as such. So we're going 3 times the 1.5. Then we are going to go minus, because this one is going to be pushing back up, causing a counterclockwise turn around this A point here. So I'm going to come across and go minus BY. Again, force times distance is our formula for solving moments. So I've got the BY multiplied by 3 meters, because that's 3 meters from that A that we are taking the moments around. We are going to come up with BY multiplied by 3, and then we're going to have that 3 multiplied by 1.5. What I would do then, I'll simply divide this side by 3 to cancel. I'll divide this side by 3, and we should get 1.5, and BY is going to equal 1.5 kilonewtons. So there, I've solved this one here. Good. Okay. Well, how then do we come back and do we solve AY? Well, that's fairly straightforward. We're just going to simply sum the forces in the Y. Our second equilibrium equation. So we're going to sum the forces in the Y equals 0. We're simply going to grab our AY, because we're including all of the forces now that are vertical. Okay, the external vertical forces. We're only just working on the reaction supports. That's why we're summing just the vertical forces, because obviously we've got this AX here, but that is going to equal 0. Why? Because there is no other external forces that are countering that one. So it must be 0. So some of the forces in Y are going to equal 0. That means we are going to have AY minus 3 kilonewtons plus the 1.5 kilonewtons. Throw that back around the other side, and we were going to get AY equals 3 kilonewtons minus 1.5 kilonewtons. AY equals 1.5 kilonewtons. And so now I've got this one here as 1.5 kilonewtons as well. And that makes sense, because up the top here you've got 3 kilonewtons pushing down. Well, you need to have, well, the forces pushing back up should be equal to that 3 kilonewtons forces that is pushing down. Okay, from here on in, we've worked out, we know that AX is going to equal 0, so we're just going to ignore that. We don't need to consider that one any further now. But we do want to start solving the internal forces of the members themselves. Okay, now we've solved those support reactions, we want to go through and solve each of the joints. So that's a fairly straightforward process. The first thing I like to do when I am doing any of these joints is to simply do my X and Y axes and label where the joints are and the forces are. Just makes it a little bit easier to solve. So we've got the sum of the forces in Y equals 0. We may as well start with that, because when I look down at this joint A, these are the forces that I've got going on. This coming in at 60 degrees. Now that is going to be called FAC, because that member here is A down the bottom and C's up the top. Okay, so I'm going to label that one FAC. This one here, or drew just a moment ago, is AY. We know that is 1.5. And then we have the other force pulling in from the joint, and that is going to be FAB force. And the reason we're starting with FY is we already know what this Y force is, so it's not going to be too difficult to calculate this only other force that has a component of Y force in it. So how do we go about that? Well, it's straightforward as well. We are going to go 1.5, pushing back up. So I've got 1.5. Then I need to take away this FAC. Why am I taking away this FAC? Because it's shooting back down. Okay, it's in a negative direction. I'm going to take FAC, but I'm only taking the Y component of that FAC. It's important to recognize that. So because I'm just taking that Y component, because I'm working the Y here, because I'm taking that Y component, what I will do, I will FAC sine 60. Remember, if I'm trying to find a force component and the angle is not between the force component, that is this Y component, and the force itself, then we are going to be signing. Now, if the angle was here, and you know what, it's pretty easy to work that out. We could say, well, obviously this is 30 degrees here, and if it was here, we could cos that 30 degrees. What we'll do, we'll take as if, no, there's nothing there. We won't do that extra working out. We'll just simply say, you know what, there's no angle here. So because there's no angle between the force and the force component we're trying to find, we are simply going to sine it. So 1.5 minus FAC sine 60, and that is all the forces that we have in the vertical or in the Y direction, okay? So that's going to equal 0. So what we'll do now, we can simply bring this over this side. FAC sine 60 equals 1.5. Let's divide that by sine 60. Cancel. Let's divide that by sine 60. 1.732. So FAC is going to equal 1.732 kilonewtons. So straight away, I can write in this FAC here. This one is 1.732. Is there anything else we need to solve? Yes, there is. We want to solve, or we can solve, the x components as well. So that means we're going to find out what this FAB is here in a moment. Sum of the forces in the x equal 0. There's two x forces. FAC cos 60, because it's coming down at that angle, at that 60 degree angle. And we're going to cos it because it's going to be pushing back that way. That's going to give us the x component of that angle. And then because that's pushing out towards the outside of the truss, then the internal member must be pulling back in to counteract that. So let's go ahead and do that. FAC, we now know what FAC is, and that's 1.732. So we'll go 1.732 cos 60, and we see that 1.732, like I said, it's pushing back in the negative, so make sure we put that negative in there. And then we've got this FAB pushing in the positive direction, so that's going to be positive. Okay, so what do? Well, we simply put FAB out in front, throw all this over the other side, and we will have our answer. The FAB is going to be 0.866. Okay, simple as that. Come back up to the top here. Just write this in, 0.866. So looking at this now, all we've got left to solve here is this member here. So what do? Well, this is just joint A we've been at so far. Okay, let's tick that. That's done. We can now come down and let's do this joint C. And you're going to see that with this problem, we're actually going to solve it. We're not going to have to visit that last joint as well, because we're going to be able to get all of our workings that we need from looking at the joint C. So get our joint C, going to put our little X and Y in. This one coming down here, which is 3 kilonewtons. The FAC that's coming up, and that is coming up like so, and that is 1.732. And then the last one that we have is going to be this one here. This, we can call that FBC. FBC is going to be pushing back up in order to counteract this 3 kilonewtons here. It's pushing down. So our FBC is coming back up. Now, we know we're told up here that we've got 60 degrees here, 60 degrees here at A and B, and obviously the triangle, 180 degrees, we know that's going to be 60 degrees up here as well. So that's all well and fine. This whole lot's 60, but if we're working just on this section here, obviously it's half of that. So we've got 30 degrees that we're going to be concerned with. So I'm just going to write in there 30 degrees. We might as well go and find our vertical components. So let's sum, remember, positive, sum of the forces in our y equals 0. We're going to come through, I'm going to go adding all our forces together, 1.732 of this one here, but that's going to be cos 30, pushing up because we're only after the y component. Okay, so cos 30. Then we're going to minus 3 kilonewtons. That's coming straight down, so we don't have to sine or cos that one. And then we come across to FBC, and that is going to be positive y because it's pushing in that positive y axis, positive y direction, plus FBC cos 30. Because we're going to bring that FBC back to that point. We want to find that y component of that FBC that is entirely on that y-axis, and so that's why we cos that 30, and then that's going to equal 0. I would bring back FBC over this side. Let's just bring that all back and make that nice and neat. FBC cos 30, oh, let me just put that cos 30 in there. Cos 30 equals, we are going to have that 3. We're going to throw it back this side, so we're going to, because we're putting it over the other side, we need to change the sense, change that negative into a positive. Then we're going to minus 1732 cos 30. 1732 cos 30, and let's get rid of this cos 30. So we get FBC by itself. We're going to have to get rid of that. We're going to have to divide it by cos 30 over here, and that is going to be FBC equals 1.732. So basically we can go back and we can hit our FBC, and we know that is now 1.732 kilonewtons. And you can see now we have solved FBC, we've solved FAB, we've solved FAC, we've got our reactions, and that's the question all over and done. I hope you found that fairly straightforward. Do watch it over again. It's one of those things, method of joints, you do need to keep watching it and really pick up what's going on. And once you get that in your mind, the process becomes just a matter of that, a process to solve the future questions. If you enjoyed this, please subscribe to my channel, and I'll be updating regularly with more engineering questions. Enjoy the rest of your day.